Chapter 4 is oscillation and waves. The first part of oscillation and waves is about simple harmonic motion. There have been questions previously on simple harmonic motions, but from looking at the papers, most of the wave characteristics and wave properties are tested more. However, understanding simple harmonic motion is crucial because a lot of students in school, they're just given the formulae and are asked to apply them. So I usually prefer going through in detail and not giving the students just the formulae to work with. So how I start off is by defining SHM. So firstly, you want to make sure the students understand what is an oscillation. So you want to tell them the idea of displacement about an equilibrium position, and that's one. And the second idea is the idea of periodicity, that the pattern repeats itself. So a simple harmonic motion is an oscillation where the displacement is can be defined by a sinusoidal curve with a constant amplitude. So whenever there is a sinusoidal curve with a constant amplitude, that is a simple harmonic motion. Now in real life, you should know that all oscillations are damped. So because of resistive forces, therefore you cannot have, therefore simple harmonic motion is an ideal case scenario. But going forward in simple harmonic motion, so let's take a case of a spring and a mass attached to the spring. Let's say mass m, and given that this mass is originally at its equilibrium position, and then equilibrium position, and then I stretch the mass to a point here. This point would be the point of maximum displacement. In other words, the amplitude of oscillation once I release the mass. So when I release this mass, it's going to oscillate between this position here, x0, and minus x0, and it will go on oscillating in a sinusoidal curve. So that would be it would describe a sinusoidal curve, and the oscillation would therefore be a simple harmonic motion. So these are the 2 points between which this mass is going to oscillate. Now, in my system here, the downward direction here is defined as positive and the upward is defined as negative. Okay? So what I do now is firstly try and get the graph of the displacement of the curve with time. So the graph of displacement versus time. So like I mentioned, the graph would be a sinusoidal function, but whether it would start off at the origin or whether it would start off at the maximum point depends on the time that I actually start my timer during this entire oscillation. So over here I'm starting the timer when the mass is at the maximum position. So therefore my curve would look like this. Okay? This is how displacement would vary with time. When one wave is complete, one complete oscillation moving from here to the topmost point and then back here, that would be one time period, and this position here, the maximum displacement, is the amplitude. Okay, now for any general sinusoidal curve, for example, x equals cosine t, let's say. Okay, for x equals cosine t, we have the curve varying between a maximum of positive 1 and negative 1. And each time the curve completes one oscillation, the t value is 2 pi. So this is in a general x equals cosine t curve. Now how do I translate this graph to that graph, firstly I need to expand it in the vertical dimension to make it oscillate between x0 and minus x0. So how I do that is simply multiplying this function with x0. Okay, so now instead of oscillating between positive 1 and negative 1, it's going to oscillate between positive x0 and negative x0. Now the second thing is, whenever my variable small t takes on the value capital T, I want the inner term here to give me 2 pi. So whenever I have a term cosine 2 pi, I would have completed one oscillation. So therefore, I need at this point small t takes on a value capital T. I need to multiply this with a value so as to get 2 pi. Okay. So the answer to that would be multiplying this with 2 pi over capital T. When I do that, whenever my small t takes on the value capital T, my term becomes cosine 2 pi and I have completed one oscillation. Okay, so therefore I get the value cosine 2 pi over capital T multiplied with small t. You see that this works well at any point. For example, at this point, I would have completed half an oscillation. Small t would take on the value capital T over 2 and I would get cosine pi. Cosine pi means half the curve. So everything fits in well. Okay? So hence the equation for this curve, for our simple harmonic motion, the displacement relates to the time via this equation. Now, whenever I have an object, for example, moving in a circle, okay, periodically, so every time it describes one complete circle, it completes one revolution, okay, one oscillation. So the frequency, in general, frequency is defined as number of waves that this object describes in 1 second. So since this object completes one wave in capital T seconds, that's the frequency. Now the another quantity is defined as omega. Omega is the angular frequency. How many radians does this object complete per second? So number of radians, or number of radians completed per second. So in one complete oscillation, there are 2 pi radians. So it completes 2 pi radians every t seconds. So that would be the angular frequency. We see that this value 2 pi over t is the same as this constant that we came up with over here. So we can simply replace 2 pi over t with omega. Therefore, our equation for displacement becomes x equals x naught cosine omega t, where omega is the angular frequency of the simple harmonic motion. Now, from here on, it's a mathematical process whereby I differentiate this entire curve with respect to time. So the students at this point should be familiar with basic differentiation. Differentiation of displacement with time gives me the velocity, and differentiating this term would give me omega x naught minus omega x naught sine omega t. Okay? So from here I can simply draw the graph of velocity versus time. Okay? So velocity versus time would roughly be a negative sine curve. Okay? A negative sine curve where this would be the completion of a time period, and the maximum and minimum values of a sine function or a cosine function are always positive 1 and negative 1. Therefore, the term in front of it, the coefficient, would give you the maximum minimum value of this curve. So the maximum value would be omega x naught. That's the maximum value of velocity. And the minimum value would be minus omega x naught. Okay? Now the same thing, differentiating this once more with respect to time, we get the value for acceleration. Now differentiating this curve gives us minus omega squared x naught cosine omega t. Okay? So this would tell us how acceleration varies with time. So that's a minus cosine curve. Okay? And the maximum and minimum value again are minus omega square x naught and omega square x naught. Okay, so these are three curves of displacement versus time, velocity versus time, and acceleration versus time. You can explain using this example to show the student where is it exactly that we have zero velocity, where is it that we have maximum velocity. We have maximum velocity at the equilibrium position, and in which direction, then the points at which we have maximum acceleration, which is at the end points, and where we have zero acceleration, which is at the equilibrium point. So you can use these three graphs to explain these concepts to the student. The next step from here would be to show the student two more graphs. Now, firstly, we can recognize that this portion here is simply x. So we can replace a equals minus omega squared x. So the acceleration is directly proportional to negative x. Okay? This is one of the defining features of a simple harmonic motion. Another way of writing this would be if I multiply both sides with mass, I get this mass times acceleration is the force. Okay, so force equals force is directly proportional to negative x. The force here that we're talking about is the restoring force, which is restoring the object in simple harmonic motion towards the equilibrium point. This force is directly proportional to negative x, which means when my displacement is positive, force is in the negative direction. When the displacement is negative, force is in the positive direction. So either this or this is the defining function, the defining characteristic of a simple harmonic motion. Okay? So this is how they can actually define SHM. In a spring, force is given as minus kx, where x is the spring constant. From here we can see that k is the same as this constant here, m, which is the mass of the object being oscillated with the angular frequency of the spring. So from here you can actually calculate the angular frequency of the spring given its spring constant. Yeah. Okay. So we have acceleration equals minus omega square x. You can see that this shows that the acceleration is linearly varying with x. If we have to draw how acceleration varies with displacement, it would just be a straight line passing through the origin. And also it would have a negative gradient of negative omega squared. This would be x naught. This would be negative omega squared x naught. Omega squared x naught and negative x naught. So this is how acceleration varies with